Hello and welcome back to making a synthesizer in C. This is episode 2. So in the first episode I made a very simple synthesizer in the C programming language and using a library called Raylib. Let's see what we made. Here it is. It's very simple. Oscillator is doing additive synthesis, so it's summing up a bunch of various sine waves, and we get this slightly square wave. It's not obviously a true square wave looking thing. Cool. So let's have a look at what we can do now. So there's a few things that I noticed I can tidy up. So let's see. Here we're calculating the frequency, and we're doing it within this loop for each oscillator. And seeing as, yes, so we're using I, but the base frequency can definitely go up to the top. We'll hoist that out. At the moment, normalized index isn't being used or anything. We'll comment that out. Okay, and there was another error I noticed when we were doing the LFO, because we were updating the LFO outside of this accumulateSignal loop. And yeah, so I noticed something was wrong when we were having to set it to a really high frequency. Just sorry. Just to get it to wobble really fast. So the problem was, I think, is that inside accumulateSignal, we're accumulating this stream buffer size. So we're doing this loop 1,024 times. So obviously, if we're updating the LFO out of that, it's going to be running 1,024 times slower. So we basically need to update that, multiply it by 1024. I'll show you what I mean. So when we do update OSC, LFO, or pointer to LFO, we need to multiply. So I think what I'm going to do, this phase stride, only ever gets used there, and we're updating the phase stride for this one in accumulate anyway. All right, I'm going to create a new function called void set os frequency, taking an oscillator and frequency, and all that does is set os phase stride equals frequency times sample duration. We need to take in the sample duration. Seeing as we've got a fixed sample rate, we can define that. Oh, there we go. We just did that. Sample rates. Hopefully that will work. Should go there. So now for this, we can just do set os frequency LFO, and let's say we want it to have 1 Hertz, 1 time a second, it's going to oscillate. But we actually need to times that by 1024. Because we're updating it outside this loop. We could take up an optional multiplier into update OSC. And we'd do that here. But I'm not going to do that. So now that we've got the LFO, we can get this. So what I'm going to do now is, so this is doing a sine wave. So let's pull that out. So we're going to have sine wave oscillator OSC, and that's just going to return. It's going to return not just nothing, but it's going to return a float. And the base frequency will add the sine wave of the LFO to it. Let's times that by 50 Hertz. Plus this, plus this, plus this. Alright, so let's see here that one. See, there we go, and now it's correct. That's doing a wobble once every second. Okay. Let's increase it. Increase the wobble. Let's do 10 times a second. So at some point, this is going to become so fast that we're basically doing frequency modulation. At which point we actually want to start updating the LFO within the accumulator loop, the bit that does it 1024 times. So just to do this roughly, it would look something like this, where we're taking the LFO, and then we'd update LFO, and then we'd have to set the modulation on the oscillator, so it'd be something like phase modulation equals sine wave osc LFO, and then within update OSC we'd sort of do plus Oscillator phase modulation. Oh, we'd have to add this field into here. Which will equal 0 by default. And now, because we're adding a potentially negative number, we do know to handle the case where if the phase goes below 0, we need to wrap it round back to 1. So we just add 1 to it. I'm gonna handle this case first. I think it matters. And then phase modulation, we also probably want another one, which is like phase modulation amplitude. And so it will be, we'd multiply the phase modulation by, let me see, phase modulation amplitude. So we got our oscillators, our non-oscillators. So for each of them, the phase modulation amplitude is going to be equal to, let's say 10 for now. So let's put this back to like, I don't know, 3 times a second. Get rid of this multiplication now, because we're going to move this. So we still got our base frequency can go back to how it was. And now our accumulator takes in the LFO. So for each oscillator, we're setting its phase stride. The phase stride of the LFO stays the same. So this we can reuse, we've been reusing this, so we'll do this here. Frequency now, I've got defined up here. I'm going to get rid of drawing the text here, get rid of this, and also the sample duration I don't think gets used anywhere anymore. There we go. This detune doesn't get used. Is it? Nope. That can go. Hoist this so it's close to. It's good to keep related bits of code as close to each other as possible, which makes it a bit easier to. So float frequency, comes base. I put const here. It means again, C loves, well, lots of programming languages loves to like shorten words, but it means constant. And it's basically saying this number within this scope never changes. It's mostly for us, the programmers, to be able to reason about our code a bit better when we're just skimming over it. We go, all right, yeah, this is a variable that never changes. So let's give this a go. Damn. What's going on there? So we're passing in set os frequency, that should be working fine. We're passing in the LFO. We update the LFO. We update the phase modulation of the oscillator. And then in update osc, just make sure that the LFO's phase modulation should equal 0 and phase modulation amplitude of the LFO itself isn't getting modulated. But for each of the oscillators, it starts off equaling 0. So phase drive plus equal phase modulation. So I have a feeling the problem is we should be. So basically, this whole line unwraps to something like this, where we got phase plus equals f for frequency times sample duration plus phase modulation, which is the LFO, so plus sine f of 2 pi times LFO phase times amplitude of the LFO amplitude. So is this even correct? Because really what we want to do is modulate the frequency by some sine function, or not multiple, not times it, but just plus or minus, which means we don't want phase for argument. All right, here's what I'm going to refactor. I'm going to say this is frequency. I'm going to just short this to frec. Then this becomes frec and frec modulation amplitude. It should just be amplitude. And then this set oscillator frequency can go, because now we're just going to set this and calculate this on the fly, because it's just a simple multiplication, should be alright. So now this just becomes os.frec times sample duration. All this can go. And then sine wave osc, because we now put the amplitude inside the oscillator, we can do times os amplitude. We'll remove the field from accumulateSignal. And then update ask. I'm going to take another parameter. It's going to call float frec modulation. We don't need to store that. We can do that here. So then it just becomes us.frec frequency modulation. And then this just becomes ask, and we pass in sine wave ask LFO. So we have the ELFO, and then we pass in that. Now that this set frequency, now setting the frequency is just set freq 3 times a second. Just do that, get rid of that line. And also ask I dot amplitude is equal to, we remove the amplitude argument, so that goes there. Right. Too few arguments on line 43. So we just need to pass in. But it does mean if we had like multiple LFOs, we could chain them. We could have LFO1, LFO2, and then this would become like LFO1, LFO2. We could do a chain, which I might do after this if this works. Let's give it a go. Field not found, phase modulation, nice. Don't need to do that anymore. Oh, we need to set the amplitude of the LFO. Again, I'm going to do 50 Hertz. There we go. So we're using the X coordinate of the mouse to control the frequencies of the base oscillator. Let's use the Y to control the LFO. So we can just say LFO frequency equals 3 plus normalized. What we now need is a normalized mouse Y, which is going to be mouse position Y divided by the screen height. Normalized mouse Y plus or minus 3. So now it goes from 0 to 6 Hertz. Let's give this a go. All right. Now there's one thing I want to do to make sure that we are streaming. Basically, I want to work out do we have enough time to calculate all this? Because in the episode 1, we were getting a few too many like weird glitchy sounds when we had too many oscillators. I think it was 128. Actually, it sounds alright. But we know, we know our sample rate, 44,100. So we should know exactly how much time we need to process a block of audio. So, let's have a look. I think there should be a timing function somewhere. Which is time. Time to time to time. Let's get time. Get frame time. Turn 7 seconds for last. I think that's just the one we want. Get time. Easy peasy. So, what's up here? So, this is going to be float, audio frame, duration. And then we're going to do const float, audio frame start time, which is just going to get time. And then the audio frame duration will just get time minus audio frame start time. And then this. So this will be the total frame time for like this entire window drawing block. And then we're going to draw text, format text, call this frame time, percentage F, yeah, come on, percentage F, and audio frame time, another percentage F. Total frame time. Let's be consistent. Total frame duration. Audio frame duration. And then I'm going to draw out 10, 10, 20, and red. Get rid of this one. See how that fares. So we can see the frame time is 0.0166, which sounds about right, because if we bring up our trusty calculator and do the reciprocal of 60 frames per second, which is 1 divided by 60, we get 0.0166. And then if we do the reciprocal of basically the FPS of the audio, which is 44,100, we get 2.267 times 10 to the negative 5. So there's going to be 5 zeros for it, and then 2267. Let's see. Well, that's impossible to read. Let's just put this back down to, say, 6. Yeah. So we need to move, basically we move the dot, so 2, 1, 2, 3, 4. I think that's correct. what we can do instead is do it as a percentage. Let me just, so this, want to divide that by sample duration. Can even do that as a percentage of the frame rate. Most we have to do double percentage because when you do percentage, it's sort of saying, all right, this is a placeholder value. But when you do double, it's like, actually, no, give me just a normal percentage character. Actually, no, because this is already... We need to multiply this by the stream buffer size. This technically needs to be the reciprocal, which then just becomes this, I think. Oh yeah. That's way too big though. Audio frame duration. Alright, let's work this out. So this is processing blocks of 1024 stream buffer size. And it needs to do that so it fills up 44,100. So basically we need to do 44,100 divided by 1024. So this needs to run 43.0066 times a second. So this becomes sample rate divided by stream buffer size. It's not wrong. $43. And this is how long a single frame of doing feel like though if I do this, don't these just cancel out? So it just becomes audio frame duration divided by sample rate. Alright. I'm just going to do audio frame duration. Not have a... Audio frame time 0.0002. thing is, we did actually get that number before, which was just this. Whatever. Does mean as we start to bump up, you can see the frame time takes longer and longer. At some point, like we did 512. Yeah, you can see it's starting to choke. That was really starting to choke. Okay. Cool. What next? What next? Why don't we try some other shapes? We've been doing a sine wave. Let's try a saw wave. So I'm just going to bring back to one oscillator. Oh, it doesn't like just having one oscillator. Why is that? Is that because the amplitude, well, the amplitude should just be 1 divided by 1. Just 1. That shouldn't happen. Non-oscillator's 1. Oh, still got this code here where we're only doing odd numbered oscillators that we did in the first episode. We'll get rid of that now. There we go. So it looks like our base frequency is too low for just one os. What's going on there? Let me just fix. Of course. Multiplying this should have been I plus 1. Because I starts at 0 and ends at the number of oscillators minus 1. This is a very typical programming problem called an off by 1 error. It's very easy to make. And it comes from that weird thing where, remember how I said arrays? So an array. Here we got an array with 4 values that I just had to label 1, 2, 3, 4. Well, if you want to get the first number in the array, we have to index it at 0. Because this number isn't the cardinal number of the slot, is how many jumps we're making. Because don't forget, the array actually only points to the very first entry. And then the number tells us how many times the processor needs to jump. So if we wanted to get number 3, we'd put in 2, because it looks at the very first one and then it jumps 1 space and 2 space and ends up at 3. So yeah, this is why often when working with arrays you get these off by 1 errors. They are easy to make. Cool. Put this base frequency back down to 15. It's more pleasing when it's like low like this. Cool. So what were we going to do? We were going to change the shape. So we got sine wave. Let's do a saw wave. Saw wave osc. So a saw wave should just look like, actually, let's do trusty Audacity. Generate a tone. This time, let's use sawtooth. Zoom in. See, it starts at -1. Well, I've halved the volume, so it's at -0.5. Then it rises up to plus, positive, and then it just drops back down to negative, rise up. And you'll notice we're already doing this. This is what our phase counter looks like. Here, we're rising, and then as soon as we get larger than 1, we drop down -1. The only difference is this phase is between 0 and 1, and we want a value that goes between -1 to +1. And that's pretty simple to do. We just need to take the phase, multiply it by 2. So now it goes from 0 to 2, and then just -1 from it. Let's just make this a little floating point to be clear. And now it goes. So we want to do saw wave, very easy. We just replace this here where accumulateSignal, saw wave osc. Let's call it sawtooth because that's what it's called in Audacity. Beautiful. You know what? Let's make the LFO frequency, because we're updating it down here. We don't need to do it twice. Even lower. You might be wondering what happens if we make this -1. It should or rather, sort of, we make this big enough. Okay, well, 0.25, so it's 1/4 of a second. Make this big enough to go into negative frequency. Was not expecting that. What I was expecting is, all right, let me try something. I'm going to set the base frequency of the main oscillator to negative. Yeah. So you notice that the lines are rising towards the right. If I make the frequency positive, they're sloping down towards the right, they're rising towards the left. So whether or not your frequency is positive or negative flips the phase. And the same should be true in if it lets me do a negative. Oh, it doesn't let you put in a negative frequency. That's a shame. But yeah, I wouldn't know how to. Well, don't record me. Right, let's go back to this. The next one we want to do is a triangle wave. Does it let you do triangle in this? No. So a triangle wave is basically exactly what you think. It goes up and then it goes down, it goes up and then it goes down. So you can almost think of it as like 2 sawtooth waves back to back. So you want the positive and then the negative and then the positive and then the negative. So how are we going to do that? So basically at phase, let's work this out. So at phase 0, it's going to be positive. And then by the time we get back to phase 1, it's going to be positive again, because that will complete a full cycle. Is that correct? Because with this, with the sawtooth wave at phase 0, we multiply 0 by 2, which is 0. So at phase 0, it's negative. And then at phase 0.5, it's 0.5 times 2 is 1 minus 1, so it becomes 0. And then at phase 1 becomes 1 times 2, which is 2 minus 1, which is 1, so it becomes positive. So actually, I think our sawtooth was slightly wrong, and we can validate this. We can validate this by just setting the frequency to 440. The LFO amplitude, we'll just set it to 0 for now. And if I did the same here, sawtooth. Oh no, it sounds still correct. Yeah, no, that's right. Because immediately after P1, we go right back to negative. So this is a full phase. Whereas a triangle wave, so we want something similar, except P 0.5 should now be positive, and P1 should be negative again. So phase 0.25 should equal 0, as should 0.75. So how can we do this? So basically we want to do this bit. Should be easy. If we want phase 0.5 to become positive 1, so obviously we just did phase times 2. When we're at phase 0.5, we're going to have positive 1, except we need to do, I have a feeling you have to do times 4 and then negative 2. I don't know why. So when phase is 0.5 times 4, we end up with positive 2. Negative 2 would now be 0. Then when phase is 0, and then when phase is 0.25, I might be going about this completely wrong. No, that's right, I think. But then we need to flip it. So it'll be something like this: if oscillator_phase is less than 0.5, then we return this. Else, we need to return a slightly different value. Which is it just negative oscillator phase? We need to, I mean, instead of doing that, we can just do -4 plus 1. So let's give this a go. So when phase is 1 times -4, we're going to get -4. Plus 1, that will give us -3, that's not right. Okay, so we want P phase of 1 to equal -1. We want just this, but we want to flip it. Let's just try this. Flip the whole thing, see what happens. So if we now do triangle wave, let me bump this down to say 50. No, 50. So it's clearly wrong. Make it a power of 2. Don't even know what's going on there. Alright, let's work this out. So I think this bit's cracked. So if we just do 0 for now, we'll get Sorry to make this alias better to the screen. Trying to find a frequency where it doesn't dance around the place. Probably easiest is just use this again. Now, so you can see it's doing the saw and then 0 and then saw and then 0. So we got half of it correct. And if we were to do this again for the other half, we would get just, it would go even lower. And if we were to flip, we do like -4. So we would have phase -4. This would then need to be +3. Yes! There you go. Beautiful. Right, we can get rid of these comments. Bring back my beautiful LFO. This is fun. So now we want to start being able to stack. I want to be able to set so one way we could do that is we could have like an enum. We have to do like type def enum, and then we could do like sine, sort, and triangle, and this would be like oscillator shape. And then this would have a shape field. But actually, if we did it this way, so this enum is basically just a way of defining a list of things that we can refer to later. Almost like if you're imagining you're making a drop-down list in a form, these are all the possible items that could be in that drop-down list. But actually my preferred way to do this would be to just have 3 arrays. So you'd have oscillator, and then I'd have sine oscillators. I would have sawtooth oscillators, and I would have the triangle oscillators. And then it can just loop over each of these in turn. Which should be a little nicer. So let's do that. It's a bit nicer for the CPU as well. Rather than doing, so if I was to have that oscillator shape in here, when it comes to this bit here, I'd have to like have a switch statement or an if statement, like if os.shape equals sine, I'll do the sine, else if the shape is equal, so do that. And that creates conditional branching, where it'll be easy if we just had 3 loops. We'll update all the sine ones in one go, then we'll update all the triangle ones, and then we'll update all the square ones. So let's do that. We'll zero them all out. And then basically for this, we now need to do go to this normalized index. All right. Before I continue implementing this, I am going to take a break and come back in a bit. So back in 1 second. All right, I am back. Right, let's look at this again. So we were second. Yep. We created. Where did I put it? Yep. So we created these 3 arrays for sine, sawtooth, and triangle. So basically, we need to do this 3 times. I'm going to take these out because we're not actually changing them for every oscillator at the moment. So we'll do that, and basically this becomes we update sine, we update sawtooth, and then we update the triangle. This becomes sine, sawtooth, and the triangle. And then we do need to set these all up. So something like this for non-oscillators. Sine of I. Amplitude, we're just going to set to we'll do the same thing where we have multiple ones. So the first oscillator will equal num oscillators minus I. And then sine ask I dot frequency equals oh, we were changing it. Well, we don't need to change the amplitude every time, but we can do that here. So sine ask I equals space for it. We do the same. Triangle. Oh, no, that's the sawtooth. Yeah. Sawtooth. And fric equals minus fric. So it's going to accumulate all these in. See how that fares. So at the moment we've only got one of each. And we actually need to times it by a third because we've got three types. So now we get this really weird mix. And if we bump up the number of oscillators in each one, bizarre. Okay, it's like a swarm of bees. Not the bees. Right, so we can now start to pull these out because obviously we're duplicating a lot of code here. So I'm going to create a function. Call this update Oscar array. So let's start pulling some of this out. So we got the oscillator. Well, we got first of all we got the signal. Then we got the oscillator. And get size t, which is from oscillators. Let's also pass in a frequency. Oh yeah, we also need to pass in the LFO. This is quite a long function, so I'm going to start putting these on new lines. So this now becomes update Oscar array, where we pass in the signal. We pass in assign oscillator, the LFO, non-oscillators, and then base frequency. This should be alright on one line. Yeah. What did I press? And then we do that 3 times on for each one, pressing the sawtooth and the triangle. Boom. So this becomes our main audio frame. So let's also hoist this out to its own function. So we can just call this handle audio stream, synth stream. What's an array to synth stream? A pointer. And then this just becomes void. Handle audio stream, stream. Maybe hoisting that out wasn't as good. This come out as well then. These might as well become defines. Don't need to cast that to flow anymore because these are already float. And then actually, let's create a new structure to handle all this stuff. So this is going to be our synth, and it's going to have basically these and it's going to have the signal. Yes, we'll take in an instance of our synth. I'm curious to see what is this audio stream. So the audio stream just contains a pointer and 3 ints. So it's actually not that big. It's not that big a structure, so I'm not going to pass it by. Yeah, just going to copy it in. Same with this. Like, these are all pointers, but I'll keep that as a pointer. Oh, and our LFO. I'm just going to have one of them. So a synth LFO. This becomes stream. Get a synth signal. Basically need to do the Rudy arrays. We don't need to. We do need to do that because the LFO is just a single object. This becomes stream. Synth signal, synth signal, synth signal. Synth signal. This audio frame duration, we can store that in there. Now I just do synth. And then it just becomes synth.lfo. Synth. Constellate amplitude equals, gonna put that into its own variable, simplify that a bit, and then we can do the same for saw and triangle. Set oscillator amplitudes. This is just a comment. So this should become synth stream. Another thing that's been annoying me actually is I'm not keeping my naming consistent. Should be underscore. This becomes synth, the audio frame duration. And we also need to pass in right to the synth. Does this run? 82. Assignment from incompatible pointer type. And 126. Synth. I've got the LFO in there. What's wrong with this? Why is it not? Synth LFO. I've been spelling it wrong now. What is it complaining about? I must be horribly misunderstanding something. Because question, can I initialize that in there? All right. Let me do sin osc equals 0. Let's just make it all in one. Signal undeclared. Ah. So what is going on here? Still got that error. Assignment from incompatible pointer type. What am I looking for? This update oscillator. Thing is, I shouldn't have to get the address. Let's do it anyway for all of that. Here's the thing. what we could do is just pass in the synth, the whole thing. So what do you point at? So we don't need to pass in the LFO. But we do need to pass in a pointer to each of the I don't know why he's complaining about that. So then it just becomes synth.signal. Synth.lfo. Google this error. That two function would be compatible. Their parameters shall have compatible types. Because of the casual type change. Another way we can do this is, rather than packing the actual thing, we can make these pointers. We could also pack like some extra information in here, like oscillators. Signal length, for example. And then we'll still have this. And then sign-off will just be sign-off, sawtooth, triangle-esque. We'll have float, signal equals stream buffer size. signal length just becomes stream buffer size. Does mean like we don't have to do this anymore. We could still just do signal. This should be screen width, screen height. These are now already pointers. Update audio stream. Signal length. This becomes synth.num oscillators for each of these. Well, I already got that data, so we don't need to pass that in. And actually, the base frequency, you could put that in there. I'm going to leave it for now, actually. So update us array, simp, we don't need to pass in non-oscillators because that's already there in simp. Accumulate signal, simp, so also I would so we do need to pass one in there, that's the frequency. Again. Alright, so it doesn't mind that. We're not getting any compiler errors. We are getting nothing. Oscillators, not oscillators, signal stream, signal, handle audio stream, giving it the synth. The audio frame duration is getting updated. This is the point where it would be handy to have a debugger. I need to create a launch file. How do you do this again? Configurations. synth.exe. What? What? Oh, did we not? Oh, synth never update. Oh, maybe calling run doesn't actually output. Let's just run it ourselves manually and synth.exe. Sorry. Build, then run, that should still work. Yep. Then if we go here, launch. There we go. Then if we come to here and put in a breakpoint. Come on. Come on, you can do breakpoints, surely. Oh, I'm probably not building the debugging symbols, which I believe is dash G, or is it dash G? Dash G. Build and run. Small jet. There we go. So now we should be able to. Unknown. Step inside. Step inside. Not getting any variables though. Let's figure this out. Debug TCC. Actually, the Raylib did come with some template projects, so we could just look at what they do in here. This is not helpful to me. Settings. Oh, it looks like they don't have a got a make file. TCC debug symbols, not GCC, TCC. Generate runtime debug information so you can Alright, that's a problem for another day. That is a problem for another day. Let us just do some good old print debugging. So printf synth sign. Basically just want to see synth sign osc 0 dot phase. Not you. Because you're not. Outputting anything. Oh yeah. So the phase is, you know, phase is changing. So let's do signal 0. Whoa. What on earth is going on there? Now let's just handle the sign. Let's 0 each of these. Yeah, I think that was a problem. We weren't initializing these arrays and zeroing them out. Cool. Where was that print we can get rid of? And then let's bump this up to 16. And then we can do things like set the now this is all well and good. We can set the sawtooth one to be a bit louder. So maybe times that by 0.2, times that by 0.7. And we can sort of make you the only thing left I'd like to fix is obviously something weird's going on with the way we're rendering the waveform. There will be a better way to do that, make it a little more stable. Alright. We've got something, we've got an oscillator that can do sine waves, sawtooth waves, triangle waves. So next time I'm going to make a note for myself. Notes. We need to fix the way the signal is rendered. And let's add a graphical user interface for controlling the oscillators. Call this to do. Alright, I'll see you in the next episode. Bye bye.